So welcome everyone. Now we are starting the Women in Quantum event in Korea, the first Women in Quantum event in Korea, which is organized by the Ministry of Science and ICT of Korean government and hosted by Quantum Information Research Support Center of Sungkyunkwan University. I'm Yeon-Wook Sung, the director of the Quantum Information Research Support Center. First, let me introduce our Minister of Science and ICT, Im Hae-soo, who will give the welcome message to everyone who are joining this celebrated Women in Quantum event. Please.
여러분 반갑습니다. 과학기술정보통신부 장관 임혜숙입니다. 2021 양자정보주간 시작을 알리는 위민인퀀텀 개최를 진심으로 축하드리며 같은 여성과학기술인으로서 이렇게 인사드리게 되어 기쁘게 생각합니다. 기본 개념조차도 이해하기 어렵다는 양자기술 분야에서 끊임없이 도전하며 성취를 이루고 계신 데니스 러프너 부사장님과 수잔 클라크 박사님, 백한희 연구원님, 그리고 임미성, 김나영, 김세정, 최은미 교수님께 존경과 환영의 마음을 전합니다. 타 분야와 마찬가지로 과학기술 분야에서도 여성들의 참여와 역할이 갈수록 확대되고 있습니다. 이는 여성과학기술인이 섬세하면서 공감 능력이 뛰어나고 팀의 다양성을 높여 유기적, 창의적으로 만드는 등 연구 성과를 성공적으로 이끌어내기 때문입니다. 여러분의 새로운 아이디어가 양자기술을 발전시키고 혁신을 앞당기는 기폭제가 되기를 바랍니다. 아울러 이번 행사가 이공계 진학을 꿈꾸는 우리 학생들에게 양자기술 분야를 이해하고 흥미를 높이는 계기가 되기를 희망합니다. 어려운 시기에 참석해주신 모든 분들께 다시 한번 감사드리며 발표자분들의 경험과 지혜가 널리 공유되어 양자기술이 한 걸음 더 미래로 나아가는 소중한 시간이 되기를 기대합니다. 감사합니다.
Thank you, Minister Im Hae-soo. Thank you for the message. And we will meet Minister during the opening ceremony session again, live. And now I hand over the session to our first session's chair, Dennis Ruppner. And please, Dennis, it's all yours now.
Hi, everyone, and thank you so much for joining us today. We're very excited to celebrate women in quantum computing in Korea, and this is the first event of this type. And for those of you to make watching easier, if you go to the upper right-hand corner of your screen where it says View, and go to the gallery view, that will make it easier to watch the event. So, pretty easy to do. So what I wanted to do is just thank you all for joining. And as you can see, we have some very accomplished speakers tonight that I'm very excited to hear from. And I hope this is going to be the start of a number of events in Korea focused on women in quantum and women and their significant contributions to quantum computing science. So thank you all for joining. And I do want to mention that I do work with a worldwide organization called Women in Quantum, and you can just simply Google it on the internet and find it, as well as I do work for INQ as the VP of Business Development. So we are going to be a little pressed for time today, so each speaker will have 20 minutes. And for the speakers, if I I'll try to remind you through chat, or otherwise I'll jump on the mic and tell you. And then also we will have a break in the middle where there's an opening ceremony for the Korea Quantum Week event. And it will be displayed on the screen so you can watch it. But it will give, for those of you that are watching this, a little break. It's a 30-minute break for the opening event. So we hope you'll stay with us throughout the program tonight, or today, I should say today. And I look forward to hearing your questions. If you want to put questions in the chat, we'd always love to see your questions. So our first speaker is Dr. Na-Young Kim, who we're very excited to have. She's coming to us. She's an associate professor at the Department of Electrical and Computer Engineering, a member of Institute for Quantum Computing and the Waterloo Institute for Nanotechnology at the University of Waterloo. I'm really excited to meet her. In her past history, prior to joining the University of Waterloo, she worked at Apple on the development of small display products, which I think must be a really exciting experience. I don't know if she'll talk about it, but I found that really intriguing. So Dr. Kim, thank you in advance, and we look forward to hearing from you.
I believe you all see my screen and you can hear me, right?
Yes.
So let's see how it goes. From curious minds to quantum innovation labs via quantum mechanics. Good morning, Korea, and good evening, America. My name is Na-Young Kim from University of Waterloo in Canada. It is exciting to join the Women in Quantum session at the 2021 Quantum Week. Thank you very much for this opportunity, invitation, and kind introduction, Dennis. Today, I'm going to share my stories, vision, and philosophy and personal lessons from the paths I've been through in the context of quantum, instead of giving you about my technical research updates and progresses, which I hope to have in future somewhere else. The invitation truly makes me to reflect my ongoing odyssey in quantum research, recalling all the lessons in many ways. As we'll see, I've been growing together the development of amazing quantum technology, witnessing remarkable discoveries and progresses inspired by genius physicists Richard Feynman, we often cite, who urges the potential of quantum machine to tackle intractable, complicated quantum machines and quantum problems efficiently and effectively. My professional education starts back to about 30 years ago when I entered to the college. When that's the year Shor proposed an efficient factoring quantum algorithm. In my second year, one day, my classmate exciting to share a paper about quantum computer at the department library, where I was busy doing the homework of ENG. It sounded like scientific fiction, another movie of Star Wars. I did not have time to discuss with him, but I remember it. I'm truly thankful for Professor Kwon, Kwon-Soo-gil, who encouraged me to stick to physics since I was struggling to continue physics or transfer to a different department at that time. But he told us to give new eyes when I took his course, the modern physics, a precursor to quantum mechanics, which became one of my favorite subjects through Professor No's systematic teaching. In 1996, one day I visited Professor Jung Sang-kim, back then as a PhD student at Stanford, who kindly showed his drill fridge, the gigantic the shoulder room, trying his best to explain his quantum single photon turnstile device. Back then, I didn't even take the quantum mechanics yet, so he was struggling. But I remember his passion and belief in quantum. In my senior years, I was teamed up with this talented two 선배s, and performing the senior experimental projects for a year, one of which is we study the very, very dim light sources. So now I remember that this is related to the non-classical light, like single photon source. I continue on to graduate schools, and Professor Shankar in quantum mechanics, he actually introduced for about 2 or 3 weeks about quantum computation using his friend's lecture notes, John Preskill's. So it's about a year ago, he published this lecture notes. So it was very fascinating that he beyond the typical textbook, and he delivered the excitements about the quantum computation. And this is the first moments I actually encountered the official quantum computation part. And that's the year the D-Wave announced that they're going to make this commercial quantum computer. Obviously, we don't believe it. Is it true? Is it a scam? And I was lucky enough to join the Professor Yamamoto's group, a sort of dream place back then, to learn quantum researches. Due to his vision, relentless pursuit, with wonderful research environment, lots of resources, and respectful and best group members. Now I'm very proud of our group alumni who lead the quantum science and technologies all over the world, especially my mentor, Professor Will Oliver, who taught me all I know now. And in 2002, when he went to this ARO, Center for Quantum Information Review meeting, and he got a feedback that your quantum electroentangler is sort of to put the elephant into the fridge. Yes, back then, still there was a skepticism about quantum computer. We always joke that the quantum computer is a millennium project. But we continue on, and I graduated by studying correlated electron transport in the context of quantum electroentangler. I failed, but I learned a lot. And that's the time Microsoft founded the Q stations as a theoretical hub for the quantum computations. And not to mention that there's a beautiful the proposal by fault-tolerant quantum computation, another genius, the Professor Kitaya. So that we are coming along. And after the graduation, I was pretty much under this DARPA quest, the quantum entanglement of science and technology. And I've been doing a lot of different projects, research projects in the context of the quantum simulators in the electronics and photonic domains. We continue, and this project is much better than 2002, the ARO, and we have a hopes. And boom, in 2014, Google announced to form Quantum Labs. And that time, many gigantic companies like IBM, Microsoft rushed to disclose their quantum research projects of commercial quantum machines. And for the last 7 years, we've been witnessing and listening the bombarding of the quantum developments towards the commercially available quantum services. And that's the moment I went to the Apple, one of the leading consumer, the world best consumer product the companies. I'm not going to talk about very much about the Apple time because I've been there only just 16 months. But that moment, I have to think. And for the last 3 decades, quantum science and technologies have been steadily and rapidly growing and mature in 3 different sectors: government, government national laboratories, academia, not to mention, and industries. These venues have their own strengths, scales, advantages, not to mention challenges and limitations. I'm very much looking forward to the talks in this session led by wonderful speakers from all 3 sectors. Personally, I've been in academia during my PhD the graduate studies and also postgraduate research step for 14 years. I had unforgettable chance to join one of the biggest consumer product, the company, the Apple. The short departure from academia put me to think deeply the meaning of research and how blessed I will be when I come back to developing the innovative and explorative and creative skills and technologies which deepen our knowledge understandings. But truly at Apple, I learned the amazing experience to think about the larger people, just beyond academia, beyond the scientists. It's the wonderful people I have to consider to serve the future. When I confronted the moments to decide for my career and the next move, I tried to look up the history, inspiring the stories of technology development and ceaseless, persistent scientists and engineers' agonies, and their efforts truly strengthened and encouraged me. These are the two examples which constantly occur to me: the fiber optics and communications, which revolutionize our modern communication, and integrated circuits certainly is essential and crucial game changer of powerful computation. So now I'm asking these questions. Is there a quantum fiber to revolutionize quantum computation? Quantum transistor to revolutionize quantum computation? Why not quantum technology be simple? Like, can we hold the quantum technology on our hands? Why not quantum technology work at room temperatures? So with these questions, I moved to Canada about 5 years ago. We are located in the northeast of the America continent and near the Great Lakes, particularly in the Ontario province. As you zoom in the map, we are very close to the U.S. border, about 1.5 hours from the Toronto, one of the biggest city in Canada, and dynamic metropolitan city. And after a pandemic is over, I really encourage you to visit us to share our excitement. And summer is especially very nice. You can see this, the actual light. We are very bright, even it's about 8:10. Institute for Quantum Computing, IQC, is in fact the first quantum institute founded in 2002 with the mission: we'd like to develop and advance quantum information science and technology at the highest international level through the collaboration of computer science scientists, engineers, mathematicians, and physical scientists. We also emphasize educate quantum generations through pedagogical curricula and outreach programs accumulated for the last 19 years. In addition, we established Waterloo's Quantum Valley by connecting academia and industries, making strong networks among University of Waterloo, Perimeter Institute, Quantum Valley Idea Labs, Lazarides Institute, and Quantum Valley Investments. Especially, we have a unique inventor-owned IP policy at University of Waterloo that greatly support our entrepreneurship in quantum. Here, I'm leading quantum information laboratory with ambitious dream that our research activities can be influential and impactful as an innovative contribution to the world. At the central heart, I appreciate the beauty and the wonder of nature. In particular, from my training and experience, I have special lenses to look at the amazing lessons nature teaches us. Throughout the varieties of conventional and exotic material, we decipher the hidden codes and properties inspired by beautiful and rigorous mathematical expressions and physical laws and principles. Upon the solid and thorough knowledge and understandings, we are able to dream how to turn our lessons into an action engineering amazing sets of technologies we all currently benefit from. At University of Waterloo, these are the people I've been closely working on a lot of different research activities. And also I have international collaborators. Now we are involved in a variety of the theoretical calculations and modeling, from condensed matter physics, band structure, and self-energy extraction, and transport and device modeling. We also look at the patterns of the radiation, and we develop some of the analysis algorithms of the sense of noise measurements. And these are really help us to move forward to the design of the actual devices. And we can also prepare the materials, and with which we can also perform the transport and optical spectroscopy measurements at low temperatures and high temperatures with the state-of-the-art experimental apparatus. So this is the everyday, the life of the Quantum Innovation Laboratory. Before the end, I'm highlighting two specific projects in the context of quantum simulator based on semiconductors, which is one of the main material. The first, Loch exoplanets are established to study the interplay of symmetry, interaction, spin, and topology in the artificial quantum materials to the quest the exotic quantum phases. We think it is the solid-state quantum simulators so that the novel quantum phases learning from this work will offer insight to the real materials and directions to synthesize functional materials for future technologies, including quantum computers. Secondly, we recently started to work on solid-state Rydberg system based on cuprous oxide, where we found the reasonable principal quantum number n up to 10 or 11 can be accessed above liquid nitrogen temperature of about 100 Kelvin. So we continue to explore what we can do this Rydberg state in semiconductors towards the mature quantum technologies by demonstrating the direct observation of Rydberg blockade as essential to define a qubit and a single photon source generation, and electromagnetically induced transparencies for qubit operations. So this is the excitement we have, so that we have a diligently preparing for our research journey, and we are really ready to look forward to the real fun continuously. And join us. We are open to people who are sincere and respectful and persistent with strong passions and convictions. So thank you very much for your attention. And if you have some questions, the remaining about 2.5 minutes, I'm more than happy to share.
Dr. Kim, thank you so much for your talk. I was interested that you left academia, went to industry, and then
Yes.
went back. And I'm just wondering how you talked a little bit about how you made the decision. Wondering if you have any further insights into that now that you've been in academia a little while, post-industry.
Yes, I think the reason I chose to go to Apple, it was also a blessing. I didn't plan it, but I always wanted to have industry experience. And then like after that, the 2014, the opportunity came, I took it. And always because the industry is imaginary. And especially Apple, because I've been there only 16 months, so that I'm not representing all the industry. And I have a small experience of the startup. But at Apple, I was involved with the extra iPhone, the 6S program. And I had to integrate the system to make the front panels of the iPhone. And in order to do so, we have to talk to the vendors who can make this the one. And one important lessons I always joking about this the experience is that the usually experimentals cannot do this the temporal the ensemble average because of the expense. But at Apple, we have millions of products. And in fact, we are able to do ensemble average to get this information. That's amazing experience. So we have to have this Six Sigma, and then the pace of the Apple development is amazing. It's beyond the imagination. It was true experience. However, the reason I come back is that during that time, I had a kind of one time I want to do the integral of the calculation, but it was so weird to have that. So it's like, I'm too young to maybe stick around this. So if I maybe more than 6 years, I will never leave Apple, but I'm too young to get used to that one. So I want to take that the much more challenging innovative research. So that's why I decided to come back. And I was also lucky to have that opportunity, and I don't regret. And I pretty enjoy that. But I also am thankful for that opportunity, so that why people like this Apple product, there are reasons.
Well, thank you for that, and thank you for a great talk. And I'm so glad she joined us. Dr. Chai is actually an assistant professor at Korea University and received her PhD in physics from Harvard and her bachelor and master's in applied physics at the University of Tokyo. She's won a huge list of prizes, including the President's Grand Prize at the University of Tokyo. So I'm very interested to hear about her research. So Dr. Chai, I'll hand it over to you. Are you on mute?
Okay, do you hear me now?
Yeah, we can hear you. Thank you.
And do you see my slides?
I see a white bar on the screen.
Can I do that?
Why don't you stop sharing and then reshare again?
Okay.
What would a meeting be without Zoom issues, right?
Yeah. I found. And you share. No, not you share, right? Okay, let me just share my desktop. How does it look right now? Is it better?
Now we see it.
Okay, great. So
Thank you.
Thank you, Dennis, for the introduction. And it is my great honor to be part of this wonderful event. So thank you very much for the invitation. So my name is Eun-mi from Korea University. And today I would like to share a new platform actually using ultra cold molecules. And so let's move on. So let me start with the famous quote of Professor Richard Feynman. So if you want to make a simulation of nature, you'd better make it quantum mechanical. So it is saying that if you want to simulate a nature phenomena such as high TC superconductor that we don't know, then you'd better make the simulator that follows quantum mechanics, because the nature is following quantum mechanics. And so that's why we are pursuing building quantum simulations these days. And some of the most important requirements for quantum simulators is that we need to control the simulators very well, because that's the merit of simulations. And also we want the simulator to be very scalable. So because we have two requirements, high controllability and good scalability, we can make a graph with two axes here. So here I have one axis with controllability and the other axis with scalability. And I put some of the main players of quantum platforms in this plot. So here is ions and superconducting qubits and neutral atoms. So these are like some of the representations of platforms. There are many more platforms, of course. And here you can see that ions and superconducting qubits have really nice controllability, but their scalability is slightly weak. Nowadays, we have about a few tens of qubits that we can control freely with these systems. And there is one more system, neutral atoms, ultra-cold neutral atoms. And here, this system has very nice scalability. We can make many, like hundreds, or in the future, thousands of qubits in the system, but the controllability compared to ions and superconducting qubits is slightly less. So, but even with these platforms, these days the research is entering very interesting phases. So we have Google has showed quantum supremacy like a few years ago. And also now people are making interesting topological phases using these quantum simulators. However, people are also pursuing a new quantum platform that satisfies both controllability and scalability. And here today, I would like to introduce a new platform that can have both controllability and scalability, which is ultra-cold molecules. So ultra-cold molecules is quite similar to neutral atoms if we want to compare like current quantum platforms. But it's similar to neutral atoms, but it's slightly more complex. So because it's similar to neutral atoms, scalability of ultra-cold molecules is guaranteed. We can make hundreds or thousands of qubits quite easily with this system. And also because they are quite similar, we can use existing technologies for atoms already. But these molecules have slightly more complex energy structure, so that such as rotational states and tensor polarizabilities and strong electric dipole-dipole interactions, we can utilize these properties of molecules to make high controllabilities of molecules. So I would like to share what's the merit of molecules in detail. So first, molecules have rotational structures that we can use as qubit systems. So because molecules have 2 or 3 nucleus, there is a degree of freedom that it rotates around an axis. And this rotational structure has energy scale of a few to tens of gigahertz, depending on the species. And it also has very long lifetime, so that it can have long coherence time. So this rotational structure is very ideal structure to be used as qubit states. So because its energy scale is about gigahertz, it can be easily controlled with existing microwave technologies. And also because it has long coherence time, we can make very efficient coupling to other platforms, such as nanophotonics and microwave circuits, which is in particularly have good properties for quantum communications. And the next merit of molecules is that it has very strong electric dipole-dipole interactions, which we can use for qubit operations. So here I put typical numbers here, and the energy scale of electric dipole-dipole interaction is in frequencies about kilohertz. So it means that we can use this strong and anisotropic interaction to make qubit operations, which is very robust because we can have this very large interaction in the ground state. So I just told you that molecules are great, but then why haven't we heard about them very much yet? So because if we want to utilize these energy scales of interactions in molecules, which is about kilohertz to megahertz energy scale, we need temperatures at around nanokelvins to microkelvin. So ultra cold temperatures are needed. And to make the molecules cold is very challenging actually. So when we say cooling molecules, as an atomic physicist, we first think about laser cooling, which is a very powerful cooling method in ultra cold atoms. So laser cooling works because photons have momentums, and as an atom absorbs the photons again and again, it slows down because of the momentum of photons. So if you want to use laser cooling, your molecules or atoms should have closed cycling transition, meaning that it should be able to scatter many photons. But however, this is very difficult in molecules because molecules have very many internal structures, such as vibrations and rotations. So therefore, if you absorb a photon, you want the electron go back to its original state, but because of the internal states, it goes to the other state and become lost. So this was the major challenge to make ultra cold molecules so far. But during the last decades, we have some breakthroughs to form a quasi-closed cycling transition. So to do that, we first choose good molecules, which is suited for laser cooling. And for that, if we have 3 lasers shining towards the molecules, we can scatter 10 to the 5 photons, which is quite enough to slow down the molecules. So using these breakthroughs, we were able to cool down molecules below 1 millikelvin. And this is actually really the cloud of molecules at around 500 microkelvin. And this, I put some of the molecules that are being laser cooled here, and you can see the years here. It's really recent advances in this field. So there are 3 kinds of molecules that are cooled below 1 millikelvin. And if once you cool down molecules below this level, we can treat the molecules just as atoms. We can control their quantum states using lasers and microwaves at our will. And we can also control their motional degrees of freedom by trapping them in optical tweezers and so on. So after we accomplished the laser cooling of molecules here, we succeeded to put the individual molecules in optical tweezer arrays like here. And then we also demonstrated the long coherence time of molecular qubits using their rotational states. So here is the recent results that we measured the long coherence time of molecules, which is reaching to 100 milliseconds, so which is very promising to be used as a new quantum platform here. So in short, I just introduced a new platform for quantum simulation, which is ultra cold molecules in optical tweezer arrays. So here is a picture, a nice illustrator of our platform. So we have optical tweezer array here, and each optical tweezer has 1 molecules in each other. And then we can manipulate these molecules using microwave easily. And then we can also use a strong electric dipole-dipole interaction to make 2-qubit operations or entanglement of 2 qubits here. And since molecules are trapped in the individual tweezers, we can control the motional degrees of the molecules nicely as well. So what I can say is that we have absolute control of molecules, all degrees of freedom in the system. And system has realized, right, really like in a few years ago. So it is very exciting moment right now that we can play with this new platform here. So what we are interested is that we can make molecular qubit system in this platform to make really quantum computing system here. Then we can also study dynamics, like quantum simulations with dynamics with long range interactions of electric dipole-dipole interaction. And also, because molecules are the basic ingredients of chemical reaction, we can also think about quantum engineering of chemical reactions in this platform. And I would like to share one of our recent experiments, which is related to this quantum engineering of chemical reaction. So here, we controlled molecular collisions. So for the chemical reactions to happen, two molecules should collide with each other. And we can control their collisions using quantum states of the molecules here. And here we use dipole-dipole interaction of the molecules and their rotational states. So here is a like simplified energy diagram of the two molecules. And we can turn on and turn off the electric dipole-dipole interaction between the molecules using microwaves. And also we can change the frequency of the microwave to make the dipole-dipole interaction repulsive or attractive. So in short, we can turn on and off electric dipole-dipole interaction, and we can also change the sign, repulsive or attractive interaction at our will. So then we used that technology to change the collisional frequency, collisional rate between the two molecules. So here we put two molecules in one optical tweezer and we shine microwave. And if we don't have any microwave, the gray line here is the molecular decay rate because of the collisions. However, when we turn on the repulsive dipole-dipole interaction, because they are repulsive, they are reluctant to collide with each other. So we see longer lifetime here as blue line here. And then if we turn on attractive dipole-dipole interaction, then we see molecules collide more frequently as in this red line. So this experiment shows you that we can indeed control the chemical reaction rate using microwaves, by manipulating molecules' quantum states. So this so far was my previous experiment at Harvard University while I was doing my PhD and also collaborating work. But I am also building a new experimental setup at Korea University. It's been about a year and a half since I've been here. So I'm building a new experiment here in Korea, and my aim or my interest of physics is quantum simulation using this new platform, new molecular platform. And also I'm interested in engineering molecular reaction, as I just showed you. And especially I'm interested in chemical reactions, which is governed by quantum statistics. So my specific molecule has bosonic species as well as fermionic species. And so I want to study how this quantum statistics, boson statistics and Fermi statistics change the reaction rate of chemical reactions as well. So, and also I'm interested in making a quantum computer, so to speak, using these ultra-cold molecules. And one of the beginning step is make 2-qubit operations. And I would like to build a 2-qubit operation using dipole-dipole interactions of molecules here. So this is the current status of my lab. So my lab is not really set up yet. We are in building phase here. So we build our molecular source here, and we prepared our new laser to laser cool our molecule. And this is actually a remarkable mark if you are familiar with lasers. We have a UV laser, CW UV laser at 359 nanometers, which produces 1.5 watts out of it. So I'm really excited to use this laser to our molecules right now. So I would like to end my talk with my dream goal of my physics life. So I would like to build a new platform for diverse quantum simulation. So as I told you before, molecules can be used as quantum computation and quantum simulations, as well as controlling chemistry. So, and I would like to broaden the species that I can trap in optical tweezers, like species of atoms and molecules, so that if we have a target Hamiltonian or a target chemical reaction, then we can find out suitable atoms and molecules that we can use as a simulator, and then we can make tailored quantum machine. That's my dream goal here. And also, this is my dream. And also by developing a new platform, we can also promote quantum computing society as well. Because if you think about development of a classical computer back in the days, it first started with vacuum gauges, right? And then people now invented a new platform using IC chips. So like this, like developing new platform will promote the overall quantum computing society, I believe. So with that, I would like to thank you for your attention.
I have a panel discussion right now with all the speakers. So I really want to thank Mi-sung and the team of people that are on the East Coast for staying with us this late. It is, I know it's, 11:30, 10:30? So thank you for staying with us. Appreciate it. One of the things that they asked us to talk about tonight was kind of how we can motivate more people to get into quantum computing, especially women. But what teaching resources do you think, would you point someone to that came to you and said, I'm interested in quantum computing, how do I start learning it? And so I was wondering, actually, Susan, I love that I'm calling on you, but I love the access that you offer to your device at Sandia. And I'm just wondering, when people come to you and ask you about education, where you steer them.
Well, the first place would probably be Dilson and Chong, the book Quantum Computing. That's still a fantastic resource. Another thing that we've been putting together at Sandia is a program for high school students for teaching quantum mechanics, and I think that program was kind of put together by Sophia Economou at Virginia Tech and Ed Barnes and Terry Rudolph, and that sort of breaks down a few simple gates in sort of an easy way, and then also sort of walks people through the Deutsch-Jozsa algorithm in kind of a fun educational way. So those are the first two things that come to mind, but there are also lots of other things like that, I think.
That sounds great. Gae-young, what do you recommend? And you're on mute.
It's Gae-young, or
Oh, I'm sorry.
are you talking to me? Not
Yes.
Okay, great. No problem. I think I'm just classifying the people who want to be invited. So certainly in an educational position, we're looking for the young generation, like high school, Susan mentioned, and also the college students. Not only for the physics major, as Susan pointed out, that the quantum computers are interdisciplinary activities, so that we are looking for the electrical engineers, mechanical engineers, and chemistry, material science, and so on. So anyone who have a basic college education, have eager to learn, then now we have amazing YouTube sources, because IQC, we have that the curricula, and also MIT develops amazing curricula for even the re-education of the engineers who are deeply in the classical field. So that's another resources. And also we have offering the outreach program for the junior students in education. So that's the one I think is easy barrier to lower down the barrier to entering, because Isaac Chuang is certainly a Bible for the quantum computer, but that would be more like an advanced level. So if we want to expand our horizon to the large crowds, then those are the resources we're gonna start with.
Okay, great. Dr. Choi, do you have any ideas of what you recommend for education?
I actually studied interface surface of semiconductor first during my master degree. So I got interested in quantum computing after hearing Yeonuk's talk in the university. And I started my research on quantum computer. At that time, and even now, there are a few materials to study quantum mechanics or quantum computing system in Korea. So I have several quantum seminars or talk on YouTube and read Nielsen and Chuang's book. And this is about other groups. Also, I have often visited websites such as IBM's Quantum Computing Guides.
Great, thank you. I didn't know you had videos. That's great. But I'm assuming they're in Korean.
Yeah.
Yeah. Okay, cool. Misan, what do you recommend for teaching, or what do you use?
Oh, yes, that's a good question, Denise. I would say that there are a lot more resources available today than it was like 10 or 20 years ago, or 30 years ago. Because back then you have to pick up books, find the right books, quantum physics or relativity, electrical engineering. There are a lot of books that you have to find, actively search, and if you didn't really come up, if you're not really coming from that kind of background, you're not exactly sure what to search. But then with the internet, there are a lot of YouTube videos where you can learn about all sorts of basics, introductions to a lot of math, physics, chemistry. There's a lot of engineering videos. There's also websites where people can ask questions. Math Stack Exchange, there's a lot of family Stack Exchange, but there are a lot of sub websites and links, and they can ask questions. I'm one of them who just go in there randomly and answer students and other people's questions. So like if I need something to do and I have nothing to do, then I'll go there and answer questions. So and they can also email professors and teachers for assistance, and they can Google for research opportunities, internship opportunities. Talk to a lot of people. Do not be afraid to talk to people. And they have to be active, and they have to search. They have to be an active learner, not just wait until someone sort of tells them, because there are so many research opportunities. Once the pandemic is over, I'm guessing a lot of the universities and Sandia National Lab and other federal labs and NSA, I'm pretty sure they'll be starting up research opportunities again. Naval Research Lab, Army Research Lab. So we have those two where they can come and do internship. They are paid internships. They can also do internships with Google, a lot of big tech companies. So there are many opportunities. So, but they have to seek out and ask. There are a lot of us. There's so many of us now, in some sense. But they do need to start reaching out to people, and then sometimes we'll guide them or introduce them to one another, like the right connections.
That's a good answer, and I do want to talk about internships in a minute. Sejong, what teaching resources or learning resources do you recommend to people?
First of all, I agree with Mi-sung that there are many available sources out there these days. So I think I agree with everyone. And also what is Na-young Kim said, it is multidisciplinary research field now. So it doesn't have, you don't have to be like expert in quantum mechanics. And one of the things I actually want to tell like younger generation is that one of the misconceptions in this field, especially in physics and quantum physics, that many people think that they have to be like genius or smart. So I think that actually
is a big barrier. So people just kind of hesitant to step into this field because when they learn quantum mechanics, it is very, very difficult. But one thing I'm sure is that you don't have to be like first grade in your quantum mechanics. You can still do research in this field because it is highly multidisciplinary field, and especially my research field because I'm more working on materials and looking for like quantum phenomenon from materials. So in my field, there are many people who's actually doing material engineering and nanophotonics, nanotechnology. So if you have any background on one of these, you can still work in quantum technology. That's it.
That's good advice. And Dr. Che, do you want to add anything to it?
Yeah, I also agree with Dr. Sejong Kim. What she said is that people are hesitant to jump into this field because it sounds difficult. And especially for like undergrad students, they usually say that my grades of quantum mechanics are not very good, so I'm not like a good people for this field. But I would like to say that like your coursework grade is not, it has some correlation, of course, but it does not say that it does not like determine your ability of research. It's sort of correlated, but if there are people whose grades are not very great, but whose research like progress is really brilliant. So I would like to emphasize like to students that don't be afraid because of your grades, and please enjoy the field first, and then if you enjoy or if you feel it's interesting, then you can learn from there step by step. So I think like fear is the most important barrier for people to overcome.
I think that's a really good point. And part of the reason why they wanted to start the Women in Quantum is to just give people some role models of different scientists with different approaches and different skill sets even, so that people can start, you know, having someone to look up to or seeing other people that they can ask advice of. I'll tell you, because I'm not a PhD in physics or math, there's a quantumcomputing.com is a great learning website. And then there's also some YouTube videos called Physics Minute, and those are pretty good too. And so I think you guys have all said, you know, go to the internet, and I think there is a lot on the internet, and it depends on what appeals to you and where you need to start out. Obviously, Nielsen and Chong is great. I think it's amazing, but I think people need to start a little earlier, or at least I did. But there's a lot of good stuff out there. The next question I wanted to ask is the second question that I get from a lot of people. So I run this group called Women in Quantum. There's probably 8,000 to 10,000 members worldwide. It's a giant mail list. There's a lot of women in quantum, but everybody is always asking me about internships and how you find an internship. So how do I come to your lab, and how do I find an internship? And is it a simple thing to write you a note, or is it a program that you're, you know, for example, and Susan, I'm picking on you, but for example, does Sandia advertise internships, or is it a question of someone writing you a note? How would people set up internships?
Yeah, Sandia is a little tricky, and particularly because there's a lot of paperwork that has to be done for anyone coming on site for Sandia. And so if it's just going to be for a summer, that might not be worth it for us. So you kind of need a longer term thing. But if there are students in our group, graduate students, and we have some undergrads in our group as well that really they reached out to their advisor who knew people, and then reached out to me or my manager or something like that and said, does this sound like something that you need? And and then and then we could pursue it. Yeah, it was kind of like a network. You got to know someone that knows someone else that knows someone else. In terms of advertising, so Sandia on their website, they do have postings for like postdoc positions and jobs, but it is really hard to search on that. So I'm sorry. Usually the best way to know about a Sandia postdoc position is to hear a talk by someone at the end who says I'm hiring and gives you the little number that you need to put into the search to find that postdoc. So otherwise, then I would say it's probably easier just to reach out to someone that might know something.
Okay, thank you. I know at INQ we had so many applicants, so many great applicants for interns, and it was very hard to pick. Dr. Misong, how do you guys take interns? Is that an issue, or how would an intern approach you? Or
So I work at West Point before coming to Annapolis, and then we do send cadets in Michigan for internships or research opportunities over the summer or like the whole semester, or maybe 1 year internship with the NSA. But then we do have internally, we have like very extensive list of all these research opportunities to go to like work at a law firm, but use a lot of mathematics, differential equations, solving systems of equations. But I saw a lot of graphs, so there's a lot of like you're asking, they're doing a lot of basically helping the firm with litigations, but you're doing a lot of mathematics, but and programming and coding. So there's a lot of really cool things, and they will pick up a lot of skills. And then I tried to set up internships with Google. They wanted to bring cadets in, but then cadets in Michigan can do only internships about 2 weeks at a time, because they have very packed schedule. So internally, we do have a lot of opportunities. MIT Lincoln Labs and the Naval Research Lab, Army Research Lab. There's a lot of opportunities. Pentagon, but then mostly those are focused towards the students. So the students will come to me and say that they're interested, and then normally I'll direct them to the director, or if it's after graduation, I'll connect them with job opportunities or internship opportunities, because I know certain people. So connect them and then let them talk. And I'm introducing them, this person has this much background, or I strongly recommend them. So I would say it's definitely connections, but we do have internally like a lot of opportunities. And then I haven't set up more internship opportunities for U.S. Naval Academy, but I tried to do them when I was at U.S. Military Academy. For like yes, I did work at Army Research Lab through National Academy of Sciences, and they gave me the opportunity to teach at West Point and do research with Army Research Lab. But to work at Army Research Lab, they have multiple facilities and it's huge. So how do you find someone compatible to work with? Because they do everything, like missile developments and helmets and armor, lighter or faster electronic devices, a lot of computing, programming, physicists, they hire mathematicians, everyone from all sorts of backgrounds, and chemists. So it was like, it comes back down to, I talked to the director, person who's organizing, I would like to do this, here's my background. So he'll circulate my CV, and then someone will say, oh, I'm interested in working with you. And then we talk a little bit and we find that we're really compatible. So it's a little bit of, so that's how my world into quantum area, sort of applied quantum, for Army Research Lab kind of went in. But then I would say it's, I have to be the one to take the initiative to say, I would like to do some research, and then go outside my comfort zone and then expand on the kind of research I want to do.
that's a good point. Also, I want to mention that INQ is near Annapolis, so we should talk.
Yes, I looked you up. Yes, you are near me, so we should come in.
So, Dr. Kim, what about internships in Australia?
Because I was in academia for my whole career, I might not be able to answer the internship opportunities in industry. So for universities, maybe postdocs and PhD positions. And other than that, we also, for example, actually visiting, getting visiting assessed is actually easier. So once you're in Australia, and if you, for example, contact one of the faculty members, and they could easily set you visitor access. And with that, although you're not being paid, but you can still get access to the lab and do some research. I think that's one of the easiest way you get some research experience.
Okay, and Dr. Che, and I'm pronouncing your name wrong, and I'm so sorry. But in Korea, can you tell us about some opportunities that you have at Korea University?
Yeah, so at Korea University, we have like, how can I say that? It's sort of an internship program for undergrads to get some experience in the labs. So we have like internship program for the summer break, summer vacation, and winter vacation for like 2 months in the labs, and they are getting like slightly paid, and they can spend some of like the whole time in the labs with the graduate students to do some specific proposed experiments in the lab. So that's very a nice way to get used to the like life in the lab. And also there are students like undergrad students who just directly contact me via email saying that they are interested in my research and can I be an intern in your lab. And then I usually accept 1 or 2 undergrad students in my lab, and then they spend time in my lab when they don't have any classes, and then they do really research in my lab. So currently I have 2 undergrad interns in my lab, and they are like really helping me out. So for like 1 or 2 months, they need some time to get used to the stuff. But after that, actually they can really make a good progress and really helping me out. So I think, and also there are like students from outside of Korea University who's reaching me out via email, and then sometimes I accept those students as well.
Dr. Young, there's a lot of education from Waterloo, and I think it's such a big program. I was wondering if you would talk a little bit about that.
Great. Yes. We have 19-year experience, so that we have a more organized way. So that for the undergraduate, every summer we have a youth school program. So that the 2 weeks for the intensive theoretical and the experimental curricula, together with the URA undergraduate research assistantship, which can last for about a term. So it's varying like 12 weeks or 16 weeks up to it. So that's a regular, so that anyone can go to the IQC Institute for Quantum Computing website, and we actually have that announcement. We collect the application. Usually our success probability of the hiring is like pretty low because we have tons of the applications. So that's the official way you could have this internship. And internally, we also have a co-op program, so the undergraduate can fully do the research work for the research only for the up to 4 months and 8 months. So that's the typical way. And in Canada, we also have a MyTex research the opportunity, which hire for the undergraduate internship, as well as the postdoctoral scholars and visiting scholars. So that's more like government level of the support, connecting with the international candidates from the developing countries and so on. So we have a lot of opportunities. As Dr. Chen mentioned out, mostly if you go to the professor's website, there are openings, and that's the place you could go and then directly talk to that. That's a kind of informal way to find this internship.
Okay, and Dr. Lee, I'm sorry I didn't call on you last question. What can you tell us about internships where you are?
In Greece, there is a 2 times per year the internship program. There is we select 2 times per year, so everybody can try. So it can be maximally 5 months, but we can be longer than So if anybody who is interested in quantum computing, superconducting quantum computing, or other system, we already have optics base or cold atom base. So if there's anybody who is interested in quantum computing, and please contact us by email, and we will find a way you can be with me.
Wow, that's great. That's great because I know for me, I worked in a lab as an undergraduate student, and that really got me motivated to go to graduate school. So I recommend that people, reach out to panelists or reach out to someone that they see on a video on the internet that's interesting, or they hear a talk that motivates them, and to reach out and form a relationship and see what opportunities there are. But I'm really excited to hear about all the opportunities in Korea. We do education every Tuesday morning, and there's quite a few people that join us, and they're all looking for more experience. So it's great to know what resources are local and what resources are overseas. We are running out of time, and so I just want to say thank you to all these ladies for joining, particularly Dr. M, because she's in Eastern time, and Dr. Young for staying with us so late. And thank you for all the preparation you did on your talks. I learned a lot. I think everybody in the audience learned a lot. And I hope that we can continue highlighting women in Korea and getting more people into the quantum computing ecosystem. So thank you. Anybody have anything they want to add before we go? All right. Thank you so much, everyone, for joining us. And thank you to Dr. Chong for putting this event together. I thought it was really a great starting point for women, and we'll hear more from the group. So thank you.
Thank you.
Thank you. Great job, everyone.
Thank you, everyone.
Thank you.